Go through practice final 1Q4. So first we're just going to go through some multiple choice about LPs. The first one is that given a two-dimensional linear program in inequality form with the objective function c transpose x with the cost vector being equal to c and the point being equal to x. As the magnitude of the cost vector c increases, the distance between the objective value contour lines increases or decreases. In this case, the distance will decrease because the contour lines pretty much represent all the points that have the same objective value. In the case that the magnitude of the cost vector will increases, the cost across the points is going to change more rapidly between different contour lines. And so that means that since the contour lines just represent a sort of gap between the different points, like of a distance of 1, the distance between the contour lines will end up decreasing because the contour lines will shift closer together. Secondly, given a two-dimensional linear program, also in the inequality form with objective c transpose x, true or false, the contour line where the objective value equals 0 always passes through the origin. This is equal to true because when our x is equal to 0, 0, the objective value c transpose x will also be equal to 0, so the contour line for the objective value that's equal to 0 is going to pass through the origin. Now we're going to go through a small sort of scenario where we have x star IP and y star IP are going to be equal to the optimal solution point and objective value of an integer program, and then x star LP and y star LP are going to be the optimal solution point and objective value for a corresponding relaxed linear program. So it's going to be the same sort of setup or LP that needs to be solved. Just in the first case, we have those integer constraints so that the solution is going to be an integer solution. Whereas for the second case, we have just the normal sort of linear programming constraints for the corresponding problem. So yeah, which of the following statements are going to be true? The first one is x star IP going to be equal to x star LP? This is false because the LP solver without the integer constraints may return a solution that's more optimal for the problem that has a better objective value in comparison to the IP solver. And so therefore the actual solutions returned by both solvers may be different, especially if the LP solution is non-integral, meaning that it might have a fractional component to it. Secondly, y star IP is going to be less than or equal to y star LP if the problem we're solving is a minimization problem. This is also false because if we're solving a minimization problem, then the LP solution is guaranteed to be at least as good as the IP solution. Since we place more constraints on the IP version of the problem, we will ultimately end up with a solution that has an objective value greater than or equal to the objective value of the solution to the LP problem. What if we flip the sign? What if we said that y star IP is greater than or equal to y star LP if it's a minimization problem? Now this is true because the LP solution has the most optimal objective value, and since this is a minimization problem, the LP solution is going to have a lower objective value than all other possible solutions, so the IP solution is guaranteed to have an objective value greater than or equal to the LP solution, which means that this is correct. Now what if we changed the setting a little bit and we're seeing maximization problems? Now in this case, would y star IP be less than or equal to y star LP? This is true, because the LP solution would have the most optimal objective value, and since it's a maximization problem, y star LP is going to be larger than all other possible objective values in terms of solutions to this problem. So the IP solution is guaranteed to have an objective value that's less than or equal to the LP solution. Finally, if we flip the sign, hopefully you see the mirror image. In this case, this inequality would be false because since this is a maximization problem, the IP solution is going to have an objective value that's less than or equal to the LP solution. Now we'll go through an example of branch and bound. So let's say we have a 3D integer program in inequality form, which is given the following setup. The setup should be familiar to you. One thing to note here is that since it's an integer program, we have this constraint that all x is going to be in the integer space, so a three-dimensional integer space. And then we have these matrices A and B that contain like the constraint sort of coefficients, and then the constraint values for each of the inequalities that are represented by the form ax is less than or equal to b. So we're going to use branch and bound to solve for the optimal IP solution. We have access to an inequality form LP solver, which is term solve LP. This takes in as input a matrix A vector B, and a cost vector C. And this also returns the optimal LP solution point and objective value for that particular linear program that A, B, and C represent. At the root node of branch and bound, the solve LP function is going to return this particular point that's given to us in terms of the solver. And because this isn't an integer solution, we choose to continue trying to find an integer solution by branching on x1. So that's going to be our first step. And once we do the branching on x1 for the left and right branch, we're going to solve LP, or we're going to call solve LP and see what solution that gives us. But what we're going to do in this problem is pretty simple. We're just going to perform the left and right branching and see how we modify our inputs. So how are we going to change A and B so that we add this like sort of constraint that x1 needs to be an integer. So if we do our left branching on x1, I guess the note here is that we want to reuse entries from the original matrix because we want to pretty much preserve those constraints that were already present on these solutions that are possible for this LP problem. And so we are going to retain all of those entries. So that's our first step. We're just going to represent, we're going to have the 4 rows that represented our original matrix A0 be part of our new matrix A. And then what we're going to do is add this new constraint for left branching. Since x1 was equal to 2.5, the left branch would be pretty much x1 is less than or equal to 2 because 2 is going to be the floor of the value that it took on in the LP solution, 2.5. And so we're just going to bound it on that left side. So x1 is going to be less than or equal to 2. So now we're going to add this constraint as part of our matrix. This bottom row here represents the coefficients. This would pretty much be equivalent to x1 plus 0 times x2 plus 0 times x3. And so this would be solving to x1 on the left side of the inequality. So then in that case, what we're going to do now is we're going to modify our b vector, which is like the corresponding side of the inequality. It's going to have one additional value. What is the new added value? Since our constraint was equal to x1 is less than or equal to 2, and our LP formulation is following that standard form ax is less than or equal to b, we're just going to add the value 2 to our original b naught vector, and that's going to give us the new b vector. So it's very similar to how we modified a. We added that extra row after preserving all the constraints from the original LP. Similarly, we're going to preserve all the values from the original b vector and make sure that we just add in that last value for that last row to represent that last constraint. Yeah, so that's left branching. Right branching is pretty much very similar to left branching, except now we're going to establish a sort of lower bound on x1 in terms of like x1 is going to be greater than or equal to the ceiling of whatever value it took on. So once again, we're going to reuse entries from the original matrix A naught. That's going to be our first step, just like constructing A naught, or in terms of constructing our new matrix A, the first 4 rows of A is going to be the same as whatever was in A naught. Now what we're going to do is add that new constraint for right branching. So instead of x1 is less than or equal to a value, we're going to have x1 is greater than or equal to the ceiling. And that ceiling for 2.5 is going to be equal to 3. So our overall constraint is going to be x1 is greater than or equal to 3. Now we want to make sure we convert this back into the inequality form that we're using in this problem. Since all the constraints were in the form ax is less than or equal to b, we can convert our greater than or equal to constraint into a less than or equal to constraint by just multiplying both sides by -1 and flipping the sign. And so that's our formulation there. We're going to take the coefficients from this inequality, which now means that the coefficient for x1 is going to be -1 because we did that flip in terms of the sign. The coefficient for the other 2 indices is still going to be 0 because they're not part of our inequality. So that's the modification we made to A. Now, after we made that modification to A, we also need to make the corresponding modification to B. So in terms of adding the value to B, we're going to retain whatever values we had from B naught in terms of the B vector. So that's going to be our first 4 values in the B vector, and then the last value is just going to be that value that represents our new constraint, or the right side of our new constraint. So since our new constraint was -x1 is less than or equal to -3, our LP formulation is going to follow that standard form ax is less than or equal to b. We're going to just add the value -3 to our original b naught vector, and that's going to give us the new b vector. Yeah, so that's pretty much it for this problem. If you have any questions, feel free to ask.